to solve another Leetcode problem. 2659. Make array empty. I think the problem is really easy to understand because there's no confusion about the description, and the description gonna be really easy to understand. So there are gonna be just two steps. So we are giving an array nums, and the numbers gonna always be distinct numbers, and we can perform the following two operations. So if the first element is the smallest value, we're going to remove it. So for example, the first element is 3 in example 1, but it is not the smallest. So we're going to just put it to the last position, because this is otherwise. Otherwise, we're going to put it at the end of the array. So we're going to put 3 at the end of the array, and this consumes one operation. And then we're going to check if this 4 going to be the smallest element. No, it is. And we're going to move it to the last, and this is going to be the second operation. And for the third operation, we're going to check if the first element is the smallest, minus 1 is the smallest, so we're going to remove it. So what's left behind is 3 and 4. So for 3 and 4, 3 is the smallest element, so we're going to remove it, so it's going to become 4. So for array 4 is the smallest element itself, so we're going to remove the last element 4, then it's going to become empty. So how many operations? So the first, second, third, fourth, and fifth operation. So after 5 operations, we get the array empty. And we should understand this kind of example. Yeah, because this is the first operation, the second operation, the third operation, the fourth operation. What left behind is 4. And then we're going to do a fifth operation. What left behind is an empty array. And similarly for the second example, so the first operation, we just remove this one. And then we're going to check if 2 is the smallest. Yes, it is. And then we left behind 4 and 3. 4 is not the smallest, so we move it at the last position. It's going to become 3 and 4. Then we're going to move 3, and we're going to move 4, and then it's going to become empty. And there are 5. Let's just check the last example. So 1 is the smallest, we remove it. 2 is the smallest, we're going to remove it. 3 is the smallest, we're going to remove it. Then it'll become empty, and it's going to be 3 operations. Basically, this is just a simulation of the problem, and because the length of the nums is 10 to the power 5, this means we cannot solve it by using the simulation of the example. Yeah, because for the simulation of example, basically we need 2 steps. So the first step is that we're gonna find the smallest element. Yeah, the smallest element, and the second step is that we're gonna remove it. Yeah, but how can we find the smallest element? So for each of the time, so for each of the time we can find the smallest element. For example, this is we can use some data structure like a dictionary or a map. We can find -1 gonna be the smallest element, because definitely we can use sorting, map, or dictionary, any kind of data structure. We can find a sequence of the smallest element to the biggest element. For example, -1, 3, and 4. Yeah, but we also should know the position, the index of this -1, 3, or 4. Yeah, but if we do not need to know the indexes, we just need to know those numbers. Maybe -1 we have an index, 3 we have an index, and 4 we have an index. But currently we just focus on the numbers itself. So for -1, because we've already found the index. So for this -1 we've already found the index, but we need to know the position of this -1. Yeah, so the index is going to be 2. It is here. So if we were to remove this -1, how many steps? So first of all, we're gonna move 3 and 4 to the last position. Yeah. So this is gonna be like O(n) time. Now we should know this is gonna be the smallest. So this is O(n) time. And for the next, another O(n) time. So how many time? It's gonna be n squared. Yeah, because we need to find the smallest element. Now we have the smallest element, but we need to shift those positions. If we only find the smallest element, it is O1. It is okay, because we can use a map to find the smallest element for each of the elements. It is O1. It is okay. But we have to move the 3 and 4 to the last position. This gonna takes O(n) time, And for each of the loop, we're gonna do this kind of operation. So in total, it's gonna be n squared, but this n gonna be 10 to the power of 5. This means we cannot use brute force to solve the problem. Yeah, so we have to turn this problem to some familiar data structure or known data structure to solve the problem. Yeah. So first of all, we're going to turn this kind of operation, the simulation, to another operation. Because currently the operation is going to be n squared, and basically we need to check if this is the smallest element. Otherwise, we're going to move it to the last position. But it is not necessary to do such operations. Maybe we don't need to do that. We can do it easier. 3, 4, and minus 1. We have 3 numbers, and for each of the number, we just need to check the index of the numbers. So, for example, for the first number, we're gonna have an index. For example, this is gonna be like a 0 for the index. Now, if this is the if this is the previous number and our current number is this number 4, so for this number 4, so the index is 1. So and for this minus 1, we have an index of 2. Yeah. So first of all, we should know what is the smallest number. It is minus 1. We can use a map with sorting, and we can find the smallest number. It is minus 1, and with an index 2, it is okay. Yeah. And now we are going to actually move this minus 1. Yeah. But we will not consider to remove a minus 1 or delete a minus 1, because definitely if the length of the array is n, how many operations for the deletion of each of the number in total? So it's going to be n times of deletion. Yeah, because there are n numbers. Definitely, if we were to delete one number, it's going to take O1 times. So in total, it's going to be n times of deletion. No, we will not consider this deletion because definitely it will be n times, but we will consider the move operation. Definitely, we need to check the numbers from the smallest to the biggest. So, for example, for first, we're gonna check this number minus 1. So for this number minus 1, as it is the smallest number, so we're gonna start from this position. Yeah, it is minus 1. Now we're gonna move this position to the next position. So where is the next position? It is 3. Yeah, because 3 is bigger than minus 1, and 3 gonna be the next number, which is bigger than minus 1. So from this position 2, we're gonna move to this position 3. Yeah, but as you can see here, this is from the last position and go to this first position, like that. Yeah, but if there are too many numbers, so we need to consider how to calculate it. Yeah. Now, from this minus 1, move to 3. How many operations do we need? We only need 1 operations. Yeah. So if we are at this position number 3, so how many operations do we need to move it to position 4? So we need another operation. Basically, we need to move from the index 0 to index 1. So we need 1 operation to move to the position 4. Yeah. So we're going to turn the problem to this problem for the numbers. If it is not the smallest, we're going to move to the last position. Yeah. So we're going to turn such problems to only consider by moving the numbers. We're going to consider to move the index. We're going to consider it is the same idea to do the simulation. So we only move the index. So from the smallest number, index 2, we're going to move to the the bigger number, which is more than minus 1. So we're going to move to index 0, and we're going to find the next bigger number, which is more than the current number 3. So it's going to be 4, and it's going to be index 1. So how many steps, so it is 1 plus 1, it's going to be 2 steps. And then we plus how many deletions. It is the total number inside of the nums array, so it's going to be 3. So 1 plus 1 plus 3, it's going to be 5. So there will be 5 operations. Yeah, but currently we didn't consider in between if there's any deletion of the number. So for example, if we want to move from 0 to 1, yeah, from the index 0 to 1, and but if the number has already been deleted, we need to consider that. Yeah, maybe let's just try to use a better example to explain it. So we're going to prepare, this is an array, this is an array, so we're going to use binary index tree to solve the problem. We have here we're going to prepare a last position. Yeah, so this means maybe this is a number like -1, and this means this may be a number 3, it is more than -1, but definitely there are many numbers in between. So this is the last position, and this is going to be the next position. So I'm going to use a position to represent in the binary index tree. Yeah. So from here, this is from the last to the current position. So if this position is more than the last position, it means in between these areas, definitely there are operations of the move operation and also the delete operation. Yeah, but we will not consider how many deletions. We only consider how can we move the numbers from the last position to the current position here. So definitely we're going to use the position is just the index, so we're going to use a position and minus the last position. So this is going to be how many operations. For example, this is the index 2, maybe this is index 4. So we're going to move from index 2 to index 4, how many operations? Because we just want to move the index, so it's going to be index 3, index 4, so it's going to be position minus the last, it's going to be how many operations. Yeah, but in between, what if for index 3, what if this number has already been what if this number has already been deleted? For example, maybe this number is -2. -2 is even less than -1. It means this number, for this number 3, at index 3, for this -2, this number actually has already been deleted. Yeah. So if this number has been deleted, so we will record it as yeah, let's just use so we're gonna record it as 1. Yeah, so this means this number has already been deleted. So we just need to check, we just need to use a query from the last index to the position. Yeah, so from the last to the position, we just need to query how many numbers have been deleted. If there's a number deleted, we're gonna record it as 1. So we're gonna use the binary index tree to add a 1. Yeah. So maybe there's one number has already been deleted. So in between the last to the position, if there are some number has already been deleted. So for move the index, we have to minus how many numbers have been deleted. Because if the number has been deleted, we don't need to consider that number anymore. So for example, if the index 3 that has been deleted, so how can we move? We can directly move from the index 2 to index 4 because that number has already been deleted. So only in this way can we simulate the operations exactly like that, because for this 4 minus 1 to 3, yeah, we move 3 to the last position. But here, it is the same idea from the last position to the position, but we just need to consider if this number has already been deleted. If it has been deleted, we're going to use a query. So we're going to use a query queue from the last position to the position. Yeah. So this is going to be the first check. If the last position is less than and equal to the position. Yeah. Let's just check another example. But there's going to be another example. The last position going to be bigger than the position, so this is going to be the last position, and this is the position in the binary index tree. Yeah, but if this last position is more than the position, this means we have to calculate it from the last and to the last index is going to be n. And here for the binary index tree, we're going to start from the 1 to position and plus last position to n. So we're going to combine those two areas. So that's going to be the condition for if the last is more than the position. Yeah. So the formula going to be n minus the last position. It is basically this areas, but we need to check how many deletions. So we're going to use a query q from the last to n. So this is one operation, and we need to plus another operation from the 1 to position. So basically, it is position minus a q from 1 to the position. Basically, it means these areas. Yeah, because from n to 1, there's another operation. So this means actually from n move to 1, there's one operation, and from 1 to position, so it's gonna be position minus 1 operation, but we need to plus another operation from n to 1, so it is a position minus 1 and plus 1, so it's gonna be a position. So basically this is for moving the index from n to position, so it's gonna be positions of move for the index, and then we're gonna minus a query from the inside of the binary tree from 1 to position, and we want to check how many deletions from 1 to position, and this is going to be the second formula. So for solving this problem, we just need to use the first formula considered with the second formula to solve the problem. Definitely we're going to use a binary index tree to solve the problem, but first of all we need to sort the numbers. We're going to use a map. We're going to sort the numbers according to the index. Yeah. So for example, we have the numbers like 3, 4, minus 1, and we need to sort the numbers like minus 1 with an index, but we need to index plus 1. For minus 1, the index is 2, but we need to plus 1 for easily using the binary index tree, because from binary index tree, we're going to always plus a 0 to the nums. At the left side, we're going to prepare 0 padding. So the index is going to be 3. This is going to be the first tuple. And the second tuple inside the map is going to be 3 with 1, because the index is 0 plus 1, it is 1. And for the third tuple, it's going to be 4. And with index, it's going to be 1 plus 1, it's going to be 2. Yeah. So this is going to be the index array. So we're going to use this index array to check to check all the possible numbers to move to make the all the number operations to make the array empty. So first of all, we're gonna check the smallest number. It is minus 1. Yeah, and then we're gonna check this number 3 and this number 4. And for here, we just record where the number it is. Where is the number? It is at index 3. It is at index 1. And here for this number, it is at index 2. Because definitely, if we wanted to do the delete operations, we're gonna use add plus a 1. It means it is the delete operations, and the position gonna be the index like 3, 1, or 2. Now let's just try to solve the problem. This is just a template for binary index tree, because for our problem we just need to use a self.tree plus the nums. I will prepare the nums later. And this is just the add operation. We're gonna add a value k to the index I for the binary index tree, and this is the sum operation. And we just need to change a little bit to make another operation. It is called query. And basically, it means from the left side, left index to the right index, both included. Yeah, it is the sum of r minus the self.sum l minus 1. So this is just a template. If you are familiar with this kind of template, Now let's just focus on the problem. So I'm going to prepare, I'm going to check the length of the array. It's going to be the length of the nums. Now I'm going to prepare the boundary index tree. It's going to be basically bit with 0 times the length of the array n. Yeah, now I prepared the boundary index tree. Basically it is here, and I put it inside prepare padding. Yeah. Now I want to prepare the result and the last position, because basically I need to just check the current position with the last position. So the last position I set it as a 1. Now I want to check. I want to prepare index array. So the index array gonna be a sorted array. So inside it's gonna be a tuple of v with I plus 1. Because for boundary index tree we prepared a padding, so I need to use index plus 1. So for iv in enumerate the nums. Yeah, so for this index array, actually it is just a mapped from the value to the index. So the first value is going to be the smallest value. It is for the value, it is basically increasing. So the array is increasing according to the first value. And for this position, I set it as a 1 because for the boundary index tree, there's a padding 0, and then I'm gonna have the real numbers. Maybe it's the 2 or 3. I'm gonna record it. Yeah, the deletions. Maybe for this one, actually it is 1. Maybe there's 1 deletions for this number, but this first number gonna be a padding. So this means I just need to record the last position as index 1 from here, because this 0 for the boundary index tree, it is just a padding. So I'm gonna start the last position as 1. So this is okay. Yeah. Now I want to check all the numbers inside the index array. So for v and position inside the index array, I want to check the position with the last position. Yeah. So if my if the last position is less than and equal to the position, basically we're gonna use the first formula. I'm not sure if I can find it. There's no. Yeah. But we're gonna use the first formula. So it's gonna be the result plus equal to. So this is the last position. Let me make a drawing. Maybe I forget. So this is gonna be the last position, and this is the position. Yeah. So this means in this areas we're gonna check how many operations. So it is the position minus the last position minus the query. So it's gonna be the position minus the last position minus the query. So the query gonna be from the last position to the position. So else we're gonna have another check. So if the position is less than the last position, it's gonna be the second formula. So this is the position, and this is the last position. Basically we need to check these areas and these areas together. So let's just use the formula. It's gonna be result plus equal to minus the last position, and minus the last position minus the query from the last position to n. So it's going to be bit.query. Yeah, and we need to another plus the first part. So the first part is going to be here from the 1 to this position. So it's going to be position minus bit.query from the 1 to the position. Yeah. So this is basically the operations. This is basically calculations of how many operations we can do to move the index. So to move the index, actually, it is just like move a lot of numbers, maybe 3 and 4 together at the end, but we just need to use one operation that is enough by moving the index. Yeah. So this is a very clever idea. So for moving the index from this L to this index P, actually, it's gonna be O(n) time. If we do the simulations like the example, we just move it to the last position. But we don't need to do that. We just need to move the index. By moving the index, it is just one operation. So we reduced the time from the O(n) to O1. This is why we're gonna use the boundary index tree. Now, I think we need to just finish the delete operation. So the delete operation is gonna be bit.add with the position. So we're gonna add 1. Actually, by adding 1, it is the deletion because we're gonna count the numbers. Because here we're gonna use a minus on the query. Yeah, and now we're gonna record the last position. It's gonna be the current position. Yeah, so we're gonna reduce the time from O(n) to O1, but we increase the time of log n. Before, the time is complexity is n squared. Now the time complexity is n log n. Yeah, although we reduced the time of O(n), but we increase the time of like a sorting. This is O(n), and like the boundary index tree, it is another log n. So the time complexity is n log n. Finally, we just need to return the result. Yeah, let me just check if there's something wrong with it. So first of all, we prepared the length of the nums and the boundary index tree, and then we need to prepare how many deletions. So it's going to be n, the length of the array. So this is going to be the last position and the index array, and we're going to compare if it is less than, and we use this kind of a first formula to check. Otherwise, we're going to use the second formula, n minus the last position, and query last position to n, and position minus from the first index to the position. And then we're gonna prepare the last position, and we're gonna prepare the deletion. Basically, it is bit.add with position to 1. If we add 1, we put 1 inside the boundary index tree. So for example, between here, we add 1. So this is 1, maybe this is 1. But while we are using query, actually from here, maybe we're gonna collect 2. Yeah, so we're gonna minus that 2 because that is the deletion. Yeah, because that 2 numbers has already been deleted. We don't need to. We have to minus, because for this operation, if this is the smallest number, it's gonna be deleted. And for here, for our boundary index tree, we have to check which number has already been deleted. If we wanted to turn the problem to just moving the index, but we need also to remember which number has been deleted, and the boundary index tree is the best data structure, or segment tree is the best structure to record such kind of a deletion. Let me run it to check. As you can see, it works. Now let me just submit it to check if it can pass. As you can see, it passed all testing cases, and it's pretty fast. Thank you for watching. See you next time.